Hello everyone. Now we are in the module 11 of the course. In this 5 lectures of 11th week, we will discuss various aspects of packaging and storage of horticultural and plantation crop product. Today, let us study what is packaging technology. In this, we will study the properties of packaging materials like mechanical, thermal, optical and barrier properties, and also we will discuss about the shelf life of packaged foods, including how to predict shelf life in packaged foods. Okay. You know, earlier also we discussed the main function of a package are to contain the product and protect it against a range of hazards which might adversely affect quality during handling, distribution and storage. The package play an important role in marketing and selling of the produce or the product. The packaging materials, various forms are used to prepare various shipping containers or retail containers. The shipping containers contain and protect the contents during transport and distribution, but they have no function in the marketing of the products, like for example, sacks, corrugated fiber, metal cases, crates, barrels, drums, etc. On the other hand, retail containers protect the food as well as advertise the food in convenient quantities for retail sale and home storage. Examples of the retail containers include metal cans, glass or plastic bottles, jar, plastic tube, trays, etc. The packaging materials, various types of packaging materials like wood, textile, metal, glass, even flexible films, plastic containers, paper and board etc. are used for making different types of either shipping containers or even the household or retail containers. And the various details of these containers as well as packaging materials used for these containers and also the packaging methods and equipment we have elaborated in lecture 19 and 20. So, I request all of you to please refer to the lecture 19 and 20 for these details. In this lecture today particularly we will discuss about the properties of the packaging materials. You know, when you are keeping in any food in a packet, whether it is a fruit, vegetable or any such commodity. So, basically this packaging material performs or package performs certain functions like it offers protection, it offers containment, it offers convenience as well as it helps in transporting, communicating or even sometimes communication, that is the labeling of the package. It gives about information about the food which is packed inside. So, basically in the packaging we create some sort of wall, that is a packaging wall, that is which in between the food and the environment, and therefore, this packaging material and packaging wall performs various functions depending upon the interactions between the package material, inside the package what is the food and the surrounding environment or environment inside the packet. Like for example, there is oxygen. Okay. So, depending upon the permeability of the packaging material, the packaging wall may allow the oxygen to go out. Okay. And if oxygen goes out inside the packet, it may catalyze oxidation reaction, color, flavor as well as this oxygen is used for respiration. Okay. When the food respires, fruits and vegetables respire, they release carbon dioxide. Okay. There may be carbonation loss and this carbon dioxide changes the environment inside and then it may be reduced, that is a shelf life etc. or it may, but if the carbon dioxide content is or so various different types of reactions may be there. So, the O2 concentration, what I am trying to say here, that packaging material should have good oxygen permeability, carbon dioxide permeability, then water vapor permeability. This when the food is dehydrated food, if in the packaged food, sometime we want that it should not regain moisture or it should not lose moisture, etc. Okay. Similarly, the aroma penetration also, that is packaging material, sometime from outside, if the packaging material of not desired, having not desired permeability to the aroma compounds, etc., then it may allow the penetration of the aroma from outside, or it may allow the out to go to the loss of the aroma from the food. Similarly, light transmission, okay, light transmission, heat sensitive products, if they are kept inside a package. So, to protect them from the light catalyzed reaction, these packaging walls would provide particular protection. Okay. Then even package component migration may be there, that is certain components from the packaging material, they may migrate into the food products. Okay. There may be absorption of the material or scalping, etc. So, these are there might be various interactions between the food, package and the environment. Okay. So, these interactions basically, as per the requirement, we try to control these interactions. Sometimes the beneficial interaction you want to encourage, and the undesirable interactions want to discourage and want to stop, and accordingly the packaging material, then properties of packaging material play a very important role in this direction. So, different properties like mechanical, thermal, optical and barrier property, and packaging material should have a proper property like mechanical property, which describes the behavior of material to mechanical forces, like example mechanical strength, density, elongation, etc. Thermal property describes behavior of material to heat, thermal conductivity, specific heat and so on. Optical property describes behavior of material to electromagnetic radiation such as refractive index, transparency, gloss and so. Barrier property describe behavior of materials to glass, transport phenomena like solubility, permeability and so on. So, let us discuss these properties, because these properties play a very important role, and one has to choose a packaging material of desirable properties depending upon what results is required, what type of the food material or fruits or vegetable is being packaged, what are its characteristics. So, in the mechanical property, first important property is tensile strength. Okay. Pattern of stress strain curve for thermoplastic is shown here in this figure. This tensile strength indicates the maximum stress that a material is able to sustain before failure. For plastic films, it is the ultimate stress. So, percent elongation at a break is calculated by reading the extension of the point of specimen rupture, dividing the extension by the original gauge length and multiplying it by 100, like elongation percent is equal to L by L0 multiplied by 100. Okay. And you can see here in this figure different points are shown. Okay. Then modulus of elasticity or Young's modulus, it is calculated by extending the initial linear proportion of the load extension curve by dividing the difference in the stress corresponding to any segment of the section on the straight line by the corresponding difference in the strain. Okay. Like stress is defined by force by area F by A, and strain is the elongation in length divided by original length. So, Young modulus becomes stress by strain. So, higher the Young modulus of a material, it indicates that the material is stiff. High Young material, Young modulus, stiff is the material. Then yield point, the stress at which the elastic material undergo increasing force and ceases to behave elastically. That is the yield point. Break point is the point that the stress at the point where the elastic specimen is ruptured, that is called break point. And impact strength is the measurement of force that is required to resist the penetration power of a rounded probe by a conditioned test practice. This property is generally considered as toughness. Impact strength could be obtained by calculating the given area of the stress strain curve before the specimen is broken or stretched. You can see that it is the break point here. Okay. There is the yield point here in this graph. Okay. That is so the elastic region. Then tear strength. This property is considered as the tear resistance, that is the force required to start tearing flexible plastic films. One side with a movable grip, that is holds the plastic sample and it stretches it at a constant rate of speed using a constant rate of grip separation test from a fixed grip. The coefficient of friction, that is this property is determined by the surface adhesivity, that is the surface tension and crystallinity, or additives which are maybe slip, pigment and anti-block agents, and surface finish. The coefficient of friction is based on the relative motion between two bodies in contact and the coefficient mu that can be expressed as a ratio of force related to the friction time from different surfaces, that is Fr is equal to mu n, where n is the normal force, Fr the frictional force, mu is the static or kinetic frictional coefficient. Then shock testing, it is very important. That is the foods in plastic containers encounter multiple forms of shock during the physical distribution when they are being transported, or during handling or lifting, or when they are being packaged, containerization, or even other forces when these other handling practices. So, various shocks depending upon the type of the packet, size of the packet, type of the food, etc. So, this testing, that is the shock testing, is important. It is done to evaluate the protective functions of the packaging system and to see the fragility of the food. Okay. The result of the product fragility test is the damage boundary curve, which provides information to the package designer about the regions where the product is more likely to be damaged. You can see here that in this region there will be no damage region. This is the critical acceleration if you give a critical velocity. So, that is the rounded figure is the damage region. Okay. So, the various forms of cushioning material therefore need to be utilized to prevent damage from outcoming. Vibration testing, I told you the vibration occurs during transportation, whether it is air transportation, maritime transportation, or on the road transportation, etc., depending upon the road conditions, other conditions. And these vibrations are highly dependent on the speed, suspensions, type of vehicle, road characteristics, or whether weather conditions, and in case of maritime shipping, etc. Okay. That in general the maritime transport produces the lower frequency vibration, followed by over the road transport, rail transport, and air transport. So, the types of vibrations may be repetitive shock vibration. It is the ideal for evaluating the escape resistance of packaging solutions, and due to their fixed frequency and fixed amplitude, limited in their ability to simulate the real world competitive vibrations. The variable frequency vibration testing is much better at simulating the complete nature of the physical distribution. It has the ability to control amplitude, frequency, and acceleration. Then let us discuss thermal properties of the packaging materials, and in this thermal conductivity and specific heat are two important properties. Thermal conductivity is a rate of heat transfer per unit area of unit thickness for unit temperature difference. Q is equal to Ka delta T by X, where K is the thermal conductivity, A is the area of cross section, X is thickness of the material, and delta T is the temperature difference. Okay, Q is the heat transfer rate. Okay. Specific heat, Q is equal to mCp delta T. Cp is the specific heat of the material, Q is the heat required, and delta T is the temperature difference. So, specific heat measures the amount of heat necessary to produce a unit change of temperature in a material. So, in this table the specific heat and thermal conductivity of different packaging materials are given, like stainless steel. You can see it has the higher thermal conductivity K value. So, it has a lower specific heat. So, wood which has a higher specific heat, maybe 2.72, it has a lower thermal conductivity. Aluminum, you see, it has the maximum thermal conductivity and it has a lowest specific heat. Then thermal expansion, that is coefficient of linear expansion alpha and volume expansion beta, express the relative change in length or volume respectively for a temperature change at a constant pressure. Okay. L is equal to L0 1 plus alpha delta T, or V is equal to V0 1 plus beta delta T, where L and B are the length and volume after temperature change, and L0 and V0 are the length and volume before temperature change, and delta T is the temperature change. Tolerable thermal resistance, the lowest limit of range is the temperature at which material shows the maximum fragility affordable during the commercial distribution, and the highest temperature is one that begins to cause a physical distortion of the object, a lack of performance or the beginning of the chemical change. So, this the lower limit and upper limit of the temperature range is another important property that is which is required, which should be considered while selecting a packaging material. For example, you see the stainless steel, its alpha, that is the linear expansion, is 13 into 10 to the power 6 mm, whereas its temperature range is lowest range is minus 45 to about 600 degree. This HDPE, it has alpha 120 and the temperature, lowest temperature minus 90 and higher temperature is 60 to 80 degree, and these temperatures are generally in degree Celsius. Okay. Then transition temperatures. Transition temperatures are the temperature at which change in the state of the substance occur under standard procedure. Okay. You can see here the graph, that stiffness versus temperature graph, and this side it shows that amorphous progressive softening or crystalline sharp melting point. Okay. So, these transition temperature, there are two, you can say that melting temperature Tm and the glass transition temperature Tg. So, the melting temperature is the temperature that correspond to the phase change from solid to liquid state. Crystalline substances, they have a sharp melting point, you can see here sharp melting point, okay, while the amorphous or non-crystalline materials have no melting point, but they soften with the heating. When they are heated, they become soft, but they may not melt. Glass transition temperature is the temperature at which a substantial change in the molecular chain mobility takes place. Plastic polymers manufactured to attain Tg above and below room temperatures are that is the Tg, these materials which have Tg below room temperature, they may be in the rubbery state and the material is flexible and soft. the material which have Tg above room temperature, they may be in glassy state and it will be a rigid material. Then we will discuss optical properties. The refractive index or refraction index is an important optical behavior, optical property, and it is according to the law of refractions or Snell's law. When a monochromatic light, as you can see here in the figure, it passes, when monochromatic light passes through a medium M1 to another medium M2, okay, of higher density, the angle of incidence, that phi 1, and the angle of refraction phi r are different, with the angle of refraction is generally lower, because the velocity of light v 1 in M1 decreases in M2. Okay. So, the n, that is the refractive index, is equal to sin phi I by sin phi r, or v 1 by v 2, that is the phi I is this angle of incidence, and then phi r is the angle of refraction. So, this property is generally used for a objective characterization of clearness of the glass and transparent plastics. Transparency, that is the fraction of light transmitted by a packaging material, is found using the Beer-Lambert law. Okay, that is IT. That is, here you see that there is a transparent material and the incident radiation is going I0 intensity from the standard light source. When it falls, that light is transmitted. I is the transmitted light. Okay. So, the fraction of light transmitted by a packaging material, that is the IT, is equal to I0 e to the power minus alpha x. IT is the intensity of light transmitted, and x is the thickness of the packaging material, and alpha is the characteristic absorbance of the packaging material. So, light transmission is required in packages that are intended to display the containers. Many times we want that inside the material, whatever is packed, in which form it is, that it should be visible to the consumer. So, in such cases transparent materials, but this it should be restricted when the food are susceptible to deterioration by light. There are certain, that the light, it is susceptible to light catalyzed reaction. So, in these cases transparent packaging should not be used. So, for example, rancidity caused by oxidation of lipid, loss of nutritional value due to destruction of riboflavin, or changes in the color caused by loss of natural pigments, etc. So, these are light catalyzed reaction. So, accordingly the material which are susceptible to these reactions, they should be packed in opaque or non-transparent containers or packaging material. So, transmission factor, that is the percent T, is calculated by, that is IT divided by I0 multiplied by 100. That is the amount of light absorbed by the food, that is I0 in a package, that is IA is equal to I0 T 1 minus RF divided by 1 minus RF RP, where RF is the fraction reflected by the food and RP is the fraction reflected by the packaging material. You can see here in the figure. Okay, I0 is falling and then I is going. Then haze is another important property, optical property. Okay, it is a degree of opacity measured in the percentage of transmitted light which deviates more than 2.5 degree from incident radiation by forward scattering in passing through a specimen. Percentage is equal to Is by It multiplied by 100, where Is is the intensity of the scattered light with the trap light, whereas the It is the intensity of the total light transmitted. Gloss is an attribute of surface which means the shiny appearance of packaging material. It is the ratio of the luminous flux reflected from the material at a specified solid angle to the luminous flux incident at the same solid range. You can see here this. Okay. Then The barrier properties of the packaging materials have significant influence on the shelf life, safety and quality of the packaged food properties. Okay. And water vapor barrier properties, gas transmission, light barrier properties, these are the primary consideration while designing a packaging material for a specific use. So, these barrier properties, particularly in fruits and vegetable packaging, they are of much utmost importance, very important. So, the permeation mechanism is a 3-step process, that is the permeate molecule from the contracting liquid phase at a partial pressure P1, okay, penetrates through the polymer surface. For pressure below 1 atmosphere, the value of the permeate concentration at the polymer interface follows Henry's law. The permeate diffuses within the polymer or packaging material from higher to lower concentration as per the Fick's law. Okay. And the permeate leaves the opposite polymer interface to diffuse in the adjacent phase, either liquid phase or gas phase at a pressure P2, that is outside is the pressure P2. Here is the C1 and here is the C2. C is the concentration, P is the partial pressure and X is the thickness of the film. Then solubility according to the Fick's law, that Na is equal to dAb C1 minus C2 by X, where Na is the flux of the gas and dAb is the diffusivity of A through B. Okay. The value of C can be correlated to partial pressure using Henry's law of equilibration, that is C is equal to Sp divided by 22.414, where C1 is Sp1 by 22.414 or C2 is the Sp2 divided by 22.414. S is the solubility coefficient and P is the partial pressure of the gas. Permeability P is a gas diffusing, that is a per cubic meter per second per square meter cross sectional area A through a 1 meter thick solid under pressure difference of delta P of 1 atmosphere pressure, and it is given by P is equal to Q multiplied by X divided by A multiplied by delta P. So, the relationship between the P, that is permeability, dAb, that is the diffusivity of A through B, and the solubility coefficient S is equal to P is equal to dAb multiplied by S. Gas transmission rate, the barrier of the film to different gases O2 and CO2 is expressed as per permeability coefficient, which expresses as amount of particular gas permeate per unit area, and the time through the unit is thickness under the pressure coefficient. So, the permeability coefficient may be for O2 it is PO2, for CO2 it is PCO2. Transmission rate is written as OTR for oxygen transmission, CO2 TR for the carbon dioxide transmission, and PO2 is equal to OTR multiply X by delta P. Similarly, PCO2 is CO2 TR multiplied by X delta P. Similarly, OTR and CO2 TR can be calculated if you know the PO2 and partial pressure difference and this thickness of the material. And these data, that is gas transmission rate data, PO2, POC2, OTR, CO2 PR, they play very important role in selecting the type of the packaging material as well as the deciding the amount of the absorbent or emitters etc., which are required to be kept inside the package in the smart packaging system or active packaging system etc. Okay. And water permeation rate, that is WVTR, the water vapor barriers RF film, is expressed as the water vapor permeability coefficient, which indicates the amount of water vapor that permeates per unit area and time through unit thickness under pressure difference, that is P permeability of H2O, that is water vapor transmission rate multiplied by X divided by delta P. or WBTR is equal to PH2O delta multiplied by delta P divided by X. So, WBTR is generally expressed in either cc or ml or gram per square meter per second. Okay. So, there are various factors which influence the permeability of a packaging material, like the chemical structure of the polymer and the permeate, that is determines the particular level of interaction. Polymer morphology, that is increase in the polymer crystallinity, that is density or orientation or cross linking decrease permeability. Okay. Then this humidity increases or decreases the permeability, especially in hydrophilic polymers. Oxygen permeability increases with the increase in relative humidity for ethylene, EBOH or nylon 6. However, oxygen permeability decreases in amorphous nylon, and increase in the temperature increases the permeability. Fillers, they increase the permeability. However, the effect is complicated by the type, shape, amount of filler and the interaction with the permeant. Okay. So, this here the effect of temperature on permeability is expressed by P is equal to P0 e to the power minus E A by RT. Okay. Diffusion through a multi-layer packaging material is described by that Na is equal to P1 minus P2 divided by 22.414, the whole thing multiplied by x1 by P1 Px1 plus x2 by Px2 or x3 by Px3. Okay. And permeability of a multi-layered packaging material, that is Pt, is expressed by x1 P3 is equal to x1 plus x2 plus x3 divided by x1 by Px1 plus x2 by Px2 or x3 by Px3, where x represents the thickness and P is the permeability of the packaging material. Okay. Then let us shelf life of the packaged food. You know that shelf life of the packaged food is controlled by the intrinsic properties of the food, extrinsic environment factor, okay, contamination by microorganism, insect or soils, mechanical forces like damage caused by the impact, vibration, compression, etc., pilferage, tempering or adulteration are the barrier properties of the packaging film. So, the packaging, they isolate the food to a predetermined degree from the environment, as I discussed earlier also. So, the package provides total protection against all these deteriorative forces. Okay. For example, in the when you sterilize the food in a canned, that is canned sterilized food, that is it has a shelf life of even several years at ambient conditions. Okay, because the packaging material is selected accordingly and also the heating process, sterilization process is chosen. So, a permeable pack is required to enable exchange of respiratory gases in respiring fresh fruits, or a simple paper bag to keep short shelf life products free from dust and insects. Okay. So, for moisture sensitive products, the moisture content of the product varies with the relative humidity at which it is in equilibrium and vice versa. The relationship between the product moisture content and the relative humidity of the head space is given by the product isotherms. Assuming that the relative humidity outside the package, that is at a storage condition, it is Pa, is constant, where the P changes through the shelf life period is a function of the product moisture content, like P is equal to P0 minus Pi(m), where m is the product moisture content on a dry basis, and this is we have assumed that the RH of the storage environment is constant. Okay. So, a differential quantity, that is the dq of water exchange through the package, is equal to the differential moisture content times the dry weight of the ratio, that is dq is equal to W multiplied by dm. Okay. Then for moisture sensitive foods, the shelf life can be written as, and it can be computed using this model, T is equal to x W by AP integral from m1 to m2 dm by P0 minus P1, where m1 and m2 refer to the product's initial and final moisture content respectively. Okay. This equation estimates the value of the product shelf life, which is defined as the time during when which a packaged moisture sensitive product remains at an acceptable or scalable conditions under specific conditions of storage. And the validity of the above equation is subject but not limiting to the conditions such as there is a fast equilibrium between the product and the package internal conditions. The delay in reaching steady state condition of permeability through the package material is neglected. The temperature and external humidity are constant through the shelf life period, and P is not affected by other permanent other permeant. So, similarly, the other models, that is this model is based upon the moisture content. Okay. Similarly, other similar models can be made, they can be designed, all right, or worked out on the basis of other suitable characteristics that and the shelf life can be predicted. Okay. So, finally, these driving forces for innovation in food packaging are the consumer lifestyle, consumer demand for products of convenience, taste good, say wholesome and nutritious, which create need and opportunity for innovation in the food packaging. Then higher benefits may also be achieved by enhancing functions of the packaging material, which satisfies the utmost needs of the consumers. Okay. It also, that is the good packaging may also help the manufacturer or producer to earn more profit. Innovative food packaging can effectively protect against microbial contamination and product tampering. That is, however, stringent regulations have been promulgated by the different countries, and this also drives research and development related to food packaging safety issues such as migration of unwanted compounds from packaging to the food and recycling of packaging materials, etc. So, finally, I will conclude this lecture. I will summarize that yes, packaging is a very important concept, particularly for fruits, vegetables, spices. The fruits and vegetables, they are highly respiring material, and even they respire during the packaging. In the next lectures, we will 2-3 lectures we will discuss in detail about the respiratory behavior, how that various active packaging, smart packaging can be done to use the shelf life extension. So, but for all these points, the selection of the appropriate packaging material, appropriate the packaging, that material characteristics, properties, that is how is the mechanical strength when this packet is being transported, it is loaded, unloaded, how it will be, the packet should not tear during the transportation, etc. How it will absorb the shock, how it will permit or transmit the flow of gases from inside to outside, outside to inside, and then light, etc. All these influence the shelf life as well as of the product inside the packet and value. So, they should be properly designed, the package should be properly designed, taking into consideration of the food characteristics, the intended shelf life, and the packaging material properties. Okay. So, this I come to the end of this lecture. These are the references which has been used in this lecture. Finally, thank you very much for your hearing.